Welcome to MSB lecture series on the chemistry of main group elements. This is 51st lecture in the series. In my last lecture, while speaking on group 16 halides, I gave information about one of the important sulfur tetrafluoride. Now, let me continue from where I had stopped. Similar to SF4, okay, disulfur dichloride. S2Cl2 is a fuming orange liquid and which is toxic and has a very repulsive smell. It is manufactured by passing chlorine through molten sulfur and further chlorination yields disulfur dichloride. It is manufactured by passing chlorine through molten sulfur and further chlorination yields disulfur dichloride. Both are essentially used, and this SCl2 as well as S2Cl2 are used for the manufacture of SOCl2. Both SCl2 and S2Cl2 are used for the manufacture of SOCl2 and SO2Cl2, and which are essentially used in the vulcanization of rubber. So, sulfur dioxide, when it is treated with disulfur dichloride in presence of chlorine, it gives SOCl2, and of course, one can also make SOCl2 starting from SO3 and its treatment with SCl2. Pure SCl2 is unstable with respect to the equilibrium between disulfur dichloride and Cl2. The structure of disulfur dichloride resembles that of S2F2, while SCl2 is a bent molecule. I can write the structure here. Okay. So, for example, this angle is 108 and this distance is 206 picometer, whereas SS bond distance is 193 picometer. Of course, as I said, it is very similar to S2F2. And in this case, this distance is 163.5 picometer and SS bond distance is little shorter, 189 picometer, and then this angle is 108.3. Okay. Decomposition of both chlorides by water yields a complex mixture containing SSO2, H2, S5O6 and HCl. And S2Cl2 is also used for the formation of a SN ring. This thionyl chloride SOCl2 and sulfuryl chloride SO2Cl2 are essentially colorless fuming liquids, and SOCl2 boiling point is 351 Kelvin and SO2Cl2 boiling point is 342 Kelvin. SO2 on treatment with PCl5 gives SOCl2, of course, through the formation of POCl3. Okay. And of course, when SO2 is treated with chlorine gas using activated charcoal, SO2, Cl2 or sulfuryl chloride is formed. Their ease of hydrolysis by water accounts for their fuming nature. What would happen if you add water to thionyl chloride? It liberates SO2 and HCl. Both thionyl and sulfuryl chlorides are commercially available. Thionyl chloride is used to prepare acyl chlorides and anhydrous metal chlorides, which are used in organometallic synthesis. Thionyl chloride structure is like this. Sulfuryl chloride structure appears like this. So, one is tetrahedral, one is pyramidal in shape. Of course, here we have a lone pair. So, this is pyramidal, whereas SO2Cl2 is tetrahedral. So, let us look into the analogous compounds of selenium and tellurium. Selenium and tellurium halides are similar to those of sulfur, but there are some notable differences. The tendency to form catenated compounds is markedly less in case of selenium and tellurium compounds. Selenium and particularly tellurium halides in plus 4 oxidate try to be polymeric. For example, tellurium tetrafluoride is polymeric, whereas selenium tetrachloride, selenium tetrabromide and also tellurium tetrachloride and tetrabromide are tetrameric. I will be showing the structure in next slide. Selenium and tellurium halides have a greater tendency to form complex anions by addition of halide anions. For example, if you consider SeCl4, one can add 1 or 2 chlorides to form minus, or one can add another one to form SeCl6 2 minus ions respectively. So, they form these kind of halide anions. Selenium tetrafluoride is a very good fluorinating agent and it is a liquid at 298 Kelvin. The isolation of diol halides of selenium and tellurium has only been achieved for selenium dichloride and selenium dibromide. Selenium dichloride is a thermally unstable red oil. Selenium dibromide is a red brown solid. For example, if you take selenium powder and treat with SO2Cl2 sulfuryl chloride at 296 Kelvin, it leads to the formation of selenium dichloride through the formation of SO2. The tellurium fluorides are prepared similarly. Tellurium tetrafluoride from tellurium oxide and SF4 or SeF4, and tellurium hexafluoride from the elements through direct combination, that is by combining tellurium and fluorine. Tellurium heptafluoride ion has a pentagonal bipyramidal structure, although in the solid state tellurium heptafluoride ion has a pentagonal bipyramidal structure in the solid state. However, equatorial F atoms deviate slightly from the mean equatorial plane. You can see here in the slide, this is how selenium and tellurium tetrachloride and tetrabromide appear like. So, having a cubane structure with alternate corners occupied by chalcogens and halogens, and with each chalcogen is hexa coordinated. So, this is the structure of tellurium tetrafluoride, which has polymeric one dimensional polymeric structure through the bridging of one of the fluorine atom between two tellurium atoms. And this is the structure of tellurium tetrachloride. This is very similar to what I have shown here. Let us look into polychalcogen cations. Oxygen with limited tendency towards catenation only forms O2 plus, but the other group 16 elements, particularly sulfur and selenium, form a range of species, some of which are shown in the next slide. Particularly sulfur and selenium form a range of species that I will show you in a minute. So, these polychalcogen cations are prepared by oxidation of the elements using strong oxidizing agents in non-aqueous solvents. For example, if you take SC8 and treat this one with arsenic pentafluoride in liquid oxygen, it leads to the formation of polychalcogen cation, the S82 plus with AsF6 minus being the counter anion. Similarly, tellurium powder on treatment with oleum, it forms tellurium 6 in its plus 4 oxygen state. So, these are polychalcogen cations. Let us look into another important set of compounds of sulfur, that is sulfur nitrogen compounds. Sulfur nitrogen chemistry is an area that has seen major developments over the last few decades because of their utility as conducting polymers. Tetrasulfur tetranitride, one of the important sulfur nitrogen compound, that is S4N4, can be readily prepared by treating S2Cl2 with ammonia. So, one can also prepare starting from this reagent. Bis trimethyl amide sulfur plus 2SCl2 plus 2SO2Cl2 gives S4N4 plus 8 Me3 SiCl plus 2SO2. So, S4N4 undergoes hydrolysis slowly by water, but rapidly when it is treated with warm alkali medium. The structure of S4N4 is a cradle-like ring in which pairs of S atoms are brought within the weak bonding distance of one another. I will be showing you soon. The SN bond distances in S4N4 indicate delocalized bonding with pi contributions. The transfer of charge from S to N also occurs, giving S delta plus and N delta minus polar bonds. One can see here. So, this is how the structure of S4N4 looks, and also when the bond is polarized, this is how you can see the weak interactions established between sulfur atoms. And S4N4 is widely used to prepare a series of compounds. A couple of compounds prepared from that one are shown here. For example, on fluorination of S4N4, it gives a puckered ring of this type. When S4N4 is treated with SnCl2 in ethanol, it gives S4N4H4. It also appears like a crown shaped ring. Okay. Now, let us look into dithionous acid, that is H2S2O4. Okay. So, only its salts are known, and these are very powerful reducing agents. Dithionate is prepared by reduction of sulphite in aqueous solution by zinc or sodium amalgam. So, in aqueous solution, dithionate anion is oxidized by air, but in the absence of air it undergoes following reaction. And if you are curious to know the structure, this is how the structure looks like. S2O4 minus, or one can also write in this fashion. So that you know where exactly the charge resides. Now let us look into two more oxo acids of sulfur, that is sulfurous and disulfurous acids, that is H2SO3 and H2S2O5. Neither sulfurous acid nor disulfurous acid has been isolated as a free acid. Salts containing the sulfite ion, that is SO3 2 minus, are well established and are very good reducing agents. For example, Na2SO3, K2SO3, which are commercially available. SO3 2 minus ion has a trigonal pyramidal structure with delocalized bonding. S2O5 2 minus ion is the only known derived anion of disulfurous acid and possesses structure with a long weak SS bond. You can see here the structures I have shown. This is sulfurous acid and this is disulfurous acid, and of course, here you can notice the two different states of two sulfur atoms. One is in +5 state, one is in +3 state. Since there is a SS bond, it is a covalent bond. So, you should not count towards the oxidation state. So, one should see here +2, +2, 4 and this one +5 and here +2 and +1. So, it is totally +3 for this one, whereas here oxidation state is +4 in case of sulfurous acid. Of course, lot of salts containing diethionate are known. Such salts can be isolated as crystalline solids, which show the presence of a long SS bond. The anion possesses a staggered conformation in the solid state. The thionate ion can be prepared by controlled oxidation of SO3 2 minus. So, that is S2O6 2 minus plus 4H plus 2 electrons will give H2SO3, and MnO2 on treatment with SO3 2 minus under acidic condition gives S2O6 dithionate anion, and the structure of this dithionic acid looks like this. Yes, yes. Okay. And when you remove this, it becomes S2O6 2 minus. Of course, sulfuric acid is very important oxo acid, and it is manufactured on a large scale by contact process. You can find in any textbook for the procedure. The first stages of this process is conversion of SO2 to SO3 and formation of oleum. The oleum is finally diluted with water to give sulfuric acid, and pure sulfuric acid is a colorless liquid with a high viscosity caused by extensive intermolecular hydrogen bonding. In aqueous solution, sulfuric acid acts as a strong acid, but the HSO4 minus ion is a fairly weak acid. So, dilute aqueous sulfuric acid, typically 2 molar, neutralizes bases and reacts with electropositive metals, liberating H2, H2SO4 For example, H2SO4 plus 2 KOH K2SO4 plus 2H2O H2SO4 aqueous solution plus CuCO3 gives CuSO4 So, concentrated sulfuric acid is a good oxidizing agent and a powerful dehydrating agent. Its reaction with HNO3 is very important for organic nitration reactions. Okay. And let us look into polyoxo acids. Although K plus salts or potassium salts of polysulfuric acids are known, they have been obtained by the reaction of SO3 with K2SO4. The free acids cannot be isolated. This salt is known. Okay, so, this has two negative charges dianionic. Let me write the structure of this polyoxo acid. Okay. Another important oxo acid is peroxosulfuric acid, that is H2S2O8. And also one more is known, H2SO5. The reaction between cold anhydrous H2SO2 and chlorosulfonic acid yields peroxomonosulfuric acid and also peroxodisulfuric acid. So, conversion of H2S2O8 disulfuric acid to monosulfuric acid occurs by controlled hydrolysis. For example, H2O2 chlorosulfuric acid chlorosulfonic acid gives H2SO5. Again treatment with another equivalent of chlorosulfonic acid liberates 1 mole of HCl to form peroxodisulfuric acid. Okay. Of course, H2S2O8 on treatment with water gives H2SO5 plus H2SO4. Okay. Both acids are crystalline solids at 298 Kelvin. Okay. And thiosulfuric acid and polythionates are also quite well known. If you want to know that peroxodisulfuric acid, the structure looks like this. Okay. Peroxodisulfuric acid means essentially you take HSO3, 2 HSO3 minus and replace 2 H of hydrogen peroxide, you get this peroxydisulfuric acid. Okay. So, one more thing is one should be familiar with the naming we use for sulfur analogues of oxygen compounds. In many cases, sulfur analogues of oxygen compounds are known, often indicated in the name by a prefix called thio. For example, I have shown some how to name this species SO4 2 minus, and if replace one of the O with S, it becomes S2O3 2 minus, it becomes thio, and then OCN minus is there, and if replace O with S, it becomes SCN minus, and similarly urea, if you replace O with sulfur, it will become thiourea. So, you can name sulfate and thiosulfate, cyanate and thiocyanate, similarly urea and thiourea, and phenol is there, and if replace O, it becomes O with S, it becomes thiophenol. So, that means wherever oxygen is there, you simply put the term thio it gives the analogous sulfur compound. Okay. So, let us look into quickly uses of group 16 compounds. Sulfamic acid is used as a precursor to make sweet tasting compounds. Reaction with cyclohexylamine followed by addition of sodium hydroxide gives sodium cyclamate. Related compounds are also sweeteners. See sulfame potassium I have shown here. Sulfamate have been used in the design of many types of therapeutic agents such as antibiotics, nucleoside, nucleotide, human immunodeficiency virus, reverse transcriptase inhibitors and anti-cancer drugs, anti-epileptic drugs and weight loss drugs. So, many of those things are used, and also they come very handy as cleaning agents. Sulfamic acid is used as an acidic cleaning agent, sometimes pure or as a component of proprietary mixtures, typically for metals and ceramics. It is frequently used for removing rust and lime scale, replacing the more volatile and irritating hydrochloric acid, which is however cheaper. It is often a component of household descaling agents. For example, lime a thick gel contains up to 8% sulfamic acid and works in the range of pH 2 to 2.2, or detergents used for removal of lime scale. When compared to most of the common strong mineral acids, sulfamic acid has a desirable water descaling properties and low volatility with low toxicity. And it forms water soluble salts of calcium and ferric ion. Importantly, sulfamic acid is preferable in household usage in comparison to hydrochloric acid for its intrinsic safety. If erroneously mixed with hypochlorite based products such as bleach, it does not form chlorine gas, where the most common acids would. The reaction with NH3 produces a salt. It also finds application in the industrial cleaning of dairy and brew house equipment. Although it is considered less corrosive than hydrochloric acid, corrosion inhibitors are often used to commercial cleaners, of which it is one of the important component. Okay. So, let me conclude the overall group 16 chemistry we learned in the last few lectures. Group 16 includes true non-metals, semiconductors and true metal in polonium. In fact, polonium is the last metal among the p block elements. So, in group 17 we do not have any metal, and of course, group 18 consists of only inert gases. Oxygen shows a maximum possible +2 state with most electronegative elements such as fluorine. Other elements form hypervalent compounds to show group oxygen state of +6. -2 oxygen state is the stable oxygen state for all elements. Catenation is very important property of sulfur, and in this aspect it is only second to carbon. Strong p-pi bonding occurs between oxygen and many other elements. Oxides of non-metals are acidic like SO3, P4, O10 etc., whereas those of metals are essentially basic. We know the difference between the properties of Na2O, CaO with SO3 or P4O10 or CO2. With this, I completed the chemistry of group 16 elements. In my next lecture, I will be starting discussion on group 17 elements. Until then, have a very pleasant reading of main group elements. Thank you very much.